Hello, everyone. Thanks for joining me. Of Clojure and a product that I'm actually very excited about called Datomic, which is a functional database. I won't get into any of that today, however, but I could talk about that stuff all day. I am a contributor to the Clojure programming language and specifically to the ClojureScript programming language, which is where the bulk of my effort has gone. And on the JavaScript side, I have contributed to something called _contrib, which is a contributor's library to the popular JavaScript library _, which perhaps some of you are familiar with. And if you follow that link, you'll be able to see some of the things that I will talk about today, and some of the things that I definitely talk about in my book, Functional JavaScript. Some relevant projects that I've worked on that I'll touch on as I go through this presentation. A library called Lemonade, which is sort of my scratch pad for exploring functional ideas in JavaScript. I don't know. The earlier version of Lemonade was taken over by the _contrib effort, but some of the work in there now is more exploratory. Really, the things that will be most relevant to this talk is the COJS library and the functional JavaScript book and the _contrib library. To start, I wanted to show a representation of a JavaScript functional program. I think if you're familiar with functional techniques, you'll agree that this is pretty representative of a functional programming approach to writing software. But of course, this is just an awesome picture. But I hope by the end of this presentation, maybe you'll feel that there's something pretty cool about functional programming. And although you may not feel quite this way about it, you might be a little bit closer there. And hopefully you'll know more about functional techniques. Thank you. So in the mid-'70s, a paper was written by someone called Richard Waters, and he described an analysis that he had done on programs written in a language called Algol. And during his analysis, he found that he noticed certain patterns that seemed to crop up over and over again in these programs. And while I'm not going to show you Algol, I will highlight the same kinds of patterns that he saw using JavaScript. The first one, if you'll see the code snippet on the screen, basically took some kind of collection and performed some kind of transformation on each element in the collection, and eventually resulting in a collection that was where each element was transformed in that way. So if I evaluate this code snippet in the browser, you'll see that the new value of transformed at the bottom is now every element in it is incremented by 100. So this was the first kind of pattern that he found in these Algol programs. And if you're familiar with underscore or even modern JavaScript, you might notice this pattern as map. Now, map is a function in modern JavaScript, and that on the array object that takes a function and applies that function to each element in the array in turn. Underscore has this function map in its library, and it takes an array and a function and does just what I said. Likewise, my library Lemonade does the same thing. Now, and those running those gives you the results that you might expect, the same as you would see in map. So another pattern that he discovered that cropped up over and over again is a way of taking a collection and applying some kind of check to each element and only keeping the things that satisfy the check. So in JavaScript, you see you could take an array and loop through the elements and only keep the ones that where the modulo of 2 is 0, which is just basically checking for evenness. So executing that, indeed, the array would have only even numbers. Again, underscore has the same kind of thing, and it's called filter. Lemonade likewise has a filter function, and those are applied in the way that adhere to that pattern that Waters discovered. Finally, the third thing that he said that he discovered that existed in these programs already was something that would run through an array or some kind of collection and accumulate some results based on a function of a sliding window over the elements in the collection. And in JavaScript, we look at that. We just have a loop that loops through an array and just sums the elements in the array. And performing that calculation shows that for every element in the original array, 1 to 5, the sum is 15. So you may already know that underscore has the same thing, and it's called reduce. And reduce indeed takes an array and a function of 2 elements, some kind of accumulator, and the element currently under inspection in the array, and just perform some operation on them. Likewise, Lemonade has the same kind of thing. It also has a reduce. There's a little bit more work to make it work in Lemonade, but like I said, I'm trying to push. It's my scratch pad. I'm trying to push functional as far as I'll go, and I won't really get into exactly what's happening there. But I think that the underscore example is probably more illustrative for this talk. Now, that was really interesting. You know that even programs sort of a long time ago were written in such a way that illustrated the use of certain techniques that even today are widely used, and you'll find these same kinds of patterns in modern JavaScript today. Now, the interesting part is that at the base of really one of the things that you could really that will really help you to understand what functional programming is all about is that these patterns are sort of materialize as these 3 basic functions: map, filter, and reduce. But that doesn't really help you to understand exactly what functional programming is all about. And to do that, I think that we can look at a language which is also a fairly old language, I believe, from the late 50s, early 60s, that sort of illustrated where functional programming really starts to shine, and that's APL. Now, there won't be a quiz to what this program's all about, but I will say that what you see on the screen is a program in APL that runs the Conway's Game of Life. So while if you're not wholly familiar with functional programming styles, I think maybe a lot of programs might look like this. But really what I'm trying to illustrate here is that, and I think where APL really gives us some guidance in understanding functional programming, is that the reason that APL was such a powerful language, if not somewhat obtuse in its syntax, is that there was a real interesting and fundamental marriage of the language with the types of data that it was meant to work on. And the types of data that APL programs were meant to work on were basically just arrays, and they took the form as multi-dimensional arrays and flat arrays, as those two images will show. So when I sat down and thought about how I would go about writing the functional JavaScript book, I thought about how could I really show JavaScript as a language that, while maybe not as functional to the core as, say, a language like Clojure or Haskell, has a lot to offer us in facilitating functional techniques. And the thing that I came to was that the JavaScript really has at its core some really interesting data structures, and we can learn a lot about functional techniques by focusing on those data structures, specifically an array and the object, and sort of use that as the basis for abstraction. And really, that's what this is all about, right? You know, if you look at this APL code, it has an abstraction too, which is the world of the game of life world. But that's, you know, just an array. But that, for the purposes of this program, is a perfectly adequate abstraction for working off of. And so functional programming, just like object-oriented programming, is an attempt to provide ways of thinking about programs and building abstractions in order to solve certain problems. So if you read my book, and I will touch on each of these points as I go along through this presentation, there's a few things that I really sort of want to get across about what it means to be to use functional programming techniques to solve problems. And the first thing that I really like to focus on is that you know, we don't have to make things overly complicated by building up large hierarchies of information like you might do in, say, a class-based system. There's a lot of things that we can do with the built-in types in a language like JavaScript that are perfectly acceptable for building abstractions out of. And likewise, so we would start with the simple data structures and small functions that work on those data structures and build up large abstractions from both those simple data types and from taking the small functions and sort of putting them, mixing them together, composing them to build larger abstractions from. Now, that's not to say that OO is bad. I mean, I'm not a OO hater. In fact, I think that especially in a language like JavaScript, object-oriented techniques can be used to supplement functional techniques very well. And in fact, I talk about that in the last chapter of the book, although I really won't get into that much here. Maybe if anyone has any questions about that, we can get into it in the Q&A part. And like I said, I'm not a hater. There's no dogma here. I think for me, the most important point is to try to get across the idea of what functional programming is at its core, and not really talk about how, you know, maybe it's not it's the be all and end all of software development, because it's not. But it's definitely a powerful tool, and we'll see. I'll try to convince you of that as we go. So let's start with simple data. Now, JavaScript has a pretty good set of core data types. Now, I'm going to use a lot of pictures in this presentation because to me, when I'm putting together something like this, I'm trying to understand something. I like to draw a lot of pictures. So if you're a visual thinker like me, perhaps this will really click with you. If not, I'm going to have some code too, and so, you know, hopefully there's something for everyone. But in JavaScript, we have some basic data types, and the first one is just a string, and I'm going to represent it as just this yellow circle with some quotes inside of it. And that'll be a stand-in pictorially for a string. Another thing is a number. And you'll see that it's similar to a string, but it's going to have this little pound sign in. So this will stand in for a number. This is our number. It's the same thing, just a way of thinking about numberness. JavaScript also has Boolean data types, and those Boolean types take the value of true and false. Now, that's not to say that those are the only thing that can be used as Boolean. In fact, JavaScript has a, let's say, rich idea of what truthiness involves. But I won't get into that into this talk. But when I do have this little symbol, it's going to mean a true false value. Excuse me. And that's all I really want it to stand in for. JavaScript's more advanced types will look like this. And to give you a hint of what exactly this is trying to convey, maybe this will help a little bit by highlighting that indeed I am showing that the array type is a fundamental type in JavaScript, a very powerful type. So to see how these things are going to all work together in my pretty pictures coming up, you can look here and see that what am I talking about here? Well, this is an array of numbers. So if you recall, it's just something like an array of 1, 2, 3, 4, 5. And finally, probably the least awesome image that you'll see in here is probably this guy, and he's going to represent JavaScript's object type. So if you squint a little bit, maybe that looks like the curly braces. But how that comes out pictorially, you'll have these things, and in JavaScript, object keys are strings, and they can map to any kind of value in the value part. But so it could look like this, but really I'm probably going to simplify it a bit and just show it with the kind of thing that is stored in the object. So this here is just an object of string keys mapped to numbers. Coming to the end of these little pictures, have a star stand in just basically to mean anything. This can be any kind of data type. So as you'll see as we go along, some functions, and JavaScript being a dynamic language, you can pass things around that without a real strict adherence to the types of things that are being passed around from function to function. But that's less a statement about that and more about a statement that says I don't really care that much about what the type of thing that we're dealing with. So moving on from small data, let me talk just a few moments about small functions. And very often in functional programming, you'll see that programmers are built up from small functions working on fairly simple data types, sort of strung end-to-end in such a way to transform data as it passes along from function to function. So you won't see very often, although you will see it in larger systems, but for the purposes of this talk, you will not see very often the use of very complicated functions or functions that run for many numbers of lines. In fact, you'll see, and I'll push this angle, is that functions very often will transform a piece of data in sort of a minor way as it takes it in and returns it from its body. But in my images, you'll see this guy, and he'll stand in for a function. because kind of, again, squinting or maybe turning your head to the side, looking at it in a mirror, or maybe, standing to one side and tilting your head. Maybe it kind of looks like what you would see. You'll see this a lot in functional programs, and that's the lambda symbol. Lambda symbol, for lack of a better explanation, usually means a function. So yeah, excuse that sort of twisted version of the lambda. But here's a function. A function that if you read it from left to right, it just says it takes an array. You remember the box means an array, and a number, and just returns something. So if we were to create a function like that, we might call it something like nth. And nth just, again, takes an array and an index in the array and just returns the index into that array. So evaluating that piece of code, that array, ABC, at the first index returns the string B. Here's another function. And this function is probably is actually kind of interesting because if you'll notice that all the way to the right of the function image, you'll have this, that you see that there's a little thing, and that's always the return type in my pictures. And so this function takes an array and another function, and that function that it takes something and returns something, and then the larger function returns an array of something. So you see how this is all sort of coming together. In fact, this function, if you're familiar with maps, this is exactly map. So this is a pictorial representation of the map function. And going back to the beginning of my talk, this is a function that takes an array and another function of two things, some things, and returns something, and at the end returns something. And if you recall, this is the reduce function that I talked about before. And finally, sort of to hammer this idea home of the images of these functions, is a function that takes an array and another function which takes something and returns a Boolean value, a truthy value. And finally, the larger function returns an array of function. Well, if you remember, this is filter. So just sort of give you a touchstone for understanding how these images are composed. So I want to go back to what I talked about before, where I want to focus on simple data. And one thing that we would like to do when building functional programs is that, or building programs using a functional style, is to take the idea of the simple data types that lie at the bottom, and what the language is indeed powerful at working with, manipulating, and building up larger abstractions from those primitives. So let's look at another image, and this is the image on the title slide. And so what is this? If you just take a moment and think about it, based on the images that I talked about before, this is an array of objects whose keys map to something, some value. But there's a larger abstraction hiding inside of this image, and I want you to try to bend your mind for just a second and think about what might that large abstraction be. And without putting too fine a point on it, I'll give you a hint. And so, here's the hint. What's the larger abstraction in that other image? Right? Okay, so it's not exactly the same thing. It is a table, right? Not that kind of table, but this kind of table. Kind of table that you might store some user information in, user ID, a name, and an age. So if you were thinking about this as being composed from simpler data types provided by JavaScript, you could see that each row in this table would be represented as an object, and the whole table itself is really just an array, a JavaScript array. And in code, that would kind of look like this, I think. And this kind of abstraction has served me very well, and I talk about this kind of thing in the book. And I think that a compelling case can be made for just keeping it simple when thinking functionally. But that's not the end of the abstraction. So an array of objects by itself is not all that useful. What we want is we want the things inside of the table. And so the abstraction highlighted here in yellow is a table cell. So while this is an entry in an object stored in an array, that's less useful than if we have a functional abstraction for this thing. What is a cell? Well, a cell is represented as a function which takes a table. I'm going to use it in a larger sense. A string and a number, and returns something. That something is the thing stored inside of that cell. So if I define a function called cell, it takes exactly those things, that table abstraction, a column, and a row. And evaluating that code would show that at the name column in the table, in the 0th element, there's Mo, and in the age there's the age 45. So these are all abstractions. Even column and row accessors are abstractions to some extent. Excuse me. But you can, thinking about data manipulation in this sort of simplistic way is a great way to think about how you would go about writing a library like I have called COJS that you would put at the bottom. You might not necessarily expose the cell, expose your data on a cell-by-cell basis, although you certainly could, and COD does. But there are more useful ways of getting at that data that I think that if you think about that larger abstraction of a table, you can do some pretty powerful things with. And so I'm going to run through a few of the things that I talked about in COD, that I implemented in COD that I think will help to highlight how thinking about data in a functional way based on data abstractions built from simple data, we can do some pretty powerful things. So this is the table that I'm going to be working off of, and this is just just a really small sample of maybe someone's iTunes library. And so there's different kinds of entries in the table, and different artists and genres and numbers of plays that for each one of these artists. Again, if we want to get at cells in that table, we can again go back to that cell function that I had showed earlier, and indeed we can start digging into that data one cell at a time. But I think that there's a more powerful way of getting at the data in here. And in COD, I build on the cell, and indeed I can show here that there's a way of building on that cell abstraction that you can build higher level ideas for accessing your data. So using that cell function, I can define a function called getArtists that takes a library and just returns every artist that it finds in that table. So running that code shows that indeed the getArtist function is, it's returning all of the artists that it finds in the table. But a function like this is very special purpose. I think that when you think functionally, you want to take the approach of looking at the larger abstractions that you have in your system and sort of pulling them apart and try to find out how can they be pulled apart in such a way that the pieces themselves are useful in isolation. In Clojure land, we would call something like that decomplecting, and without getting too deeply into what that means, basically, let's just say that that decomplecting is a way of taking apart a larger process and breaking it down into smaller processes. So where a process here would be the getArtist function, there are lower level processes hiding inside of it. And one of those is a function in COD called project. Now, the COD library, I skipped over this earlier, but I think it's worth mentioning now, is that it's a library that provides some tools and functions that offer relational algebra functions providing relational algebra to JavaScript. And while that sounds kind of fancy, relational algebra is really the stuff that lies at the bottom of your databases. And the project function can be thought of as analogous to, say, a database select statement. So here's a piece of code that shows how project works. So it takes a library, takes that table abstraction in an array, and in the array it takes one or more strings that represent the columns that we're dealing with. So if we wanted to get all of the artist entries in that table, we could pass it to project, and you'll see that project would return another table. So this is the same thing that we passed into it. So this first result here is really kind of key in understanding functional programming and building abstractions using functional styles, is that when programming functionally and returning and passing pieces of data from one function to another, it's often critical to keep in mind that it is critical to keep in mind that the types of data that's passing in between the functions. And a lot of the power that comes in the COD library is that it works off of a single abstraction, and it doesn't break that abstraction. In fact, all of the functions work off of the same abstraction, taking that table abstraction and returning table abstractions. And I think the more that you get into functional programming, the more that you'll see that the ways that programs are structured is keeping stable abstractions, keeping abstractions stable from one function, one process to another. In fact, I won't talk about monads in this talk, but I think that's one thing that really lies at the basis of what makes monads so strong, is that there's people are often striving to keep keep a stable abstraction flowing between function to function, even if those functions were never meant to compose. So that's part of what monads give. But this is not a talk about monads. I think that's a completely different talk, one that people who are far more knowledgeable than me could give. So anyway, going back to project. Project again keeps that stable abstraction, and you'll see as we go on that that the stability of the abstraction is sort of key as we build up into higher level abstraction. So project is sort of not at the bottom. It's built on top of cell, and things will be built on top of project. So I did want to mention that, like I said, that the array that gets passed into project can have any number of keys in it, and so it will look up multiple things, and so we can build on top of that, and I will. And like I said, this is relational algebra, which is pretty analogous, and in a lot of ways can be mapped to the kinds of things that you might do when writing database queries. So looking at project, this is the kind of thing that you would do. And I apologize if you're not terribly familiar with SQL, but I think that a lot of people are, and so I put it in the slide to sort of illustrate the kind of data access that project is providing. So the cool thing about working off of this lower level, building up an abstraction like a table on the base data types that JavaScript provides is that now you can pass that type into functions that work off of the base data types, even though they have no idea what you're passing in is a table. And so what that means is there's this function in underscore called sort by that just takes an array and sorts its elements, sorts the objects in the array based off of the one or more of the keys inside of contained inside of the object. Now, underscore was written long before COD was written, and it doesn't work off of anything like a table abstraction. But what it does work off of is an array of objects. And so I think this is kind of hearkening back to the APL example that said, and we want to take advantage of the existing facilities in the language to build our larger abstractions out of, because we don't want our data to be housed inside of silos or exist on an island that only a privileged set of methods can operate on. We want the full range of libraries that can work off of those base data types, and there are a lot out there, not just underscore, to work off of that data just as well as any other piece of data. So so looking at that call, the project function passed into sort by is analogous to an SQL query that would say, select these columns from the database and order by a certain column. And I think that's kind of nice how that works out. So another function inside of COD, again built off of that cell abstraction, and the table abstraction is called rename. And this gets a little bit hard to look at as you start stringing functions end to end like this, and that's somewhat of a common complaint when people look at functional programs and they say, oh, it gets really hard to look at these long strings of functions, and I can appreciate that. Although there are definitely ways to handle that, which I'll talk about later on in this talk. But in any case, let me say that this function, these calls are somewhat straightforward. It'll be a little bit harder to reason about as we go along, but I'll pull it together at the end, I promise. So the COD project function, as I talked about before, we'll pull out certain columns and populate a new table with the values in those columns. And the rename function takes a table abstraction, and an object that defines the mappings of how to rename certain keys to other values. So what it's going to do is it's going to take that project, the results of that project, and rename all instances of the key artist into band. And it's going to return another table from that. Now, the result of that rename is again passed into the sort by. And as you see, the results of executing this is indeed another table where now artist keys are now replaced by band. Now, that seems kind of pointless, right? But we do that all the time when we write SQL queries. We're selecting artist and renaming it as something else, and we're ordering it. Obviously, ordering is a critical function in SQL. So the third function that I'll talk about is called restrict. Now, restrict, it's an interesting fact about relational algebra is that the inventor, Ted Codd, he had these names like project and rename and restrict. And the SQL that's built on top of those ideas actually changed the names around. And so what was select is project, and what was project is now, it's gotten all twisted up over time, is my point. But these sort of wacky names, do have a precedent in history, and they map directly to the kind of ideas that we're using every day in our databases. But in any case, the restrict, you'll see, takes a table, but first we're going to go ahead and get the projection, rename some of the keys as before, and then the restrict function actually takes another function, a table and a function, and performs some check on each of the entries in the table. And so what restrict is doing here is it's taking that function and it is applying to each one. It's actually a misnamed. It shouldn't say cell. It should probably say something like row if I wanted to be more appropriate here. So, but in any case, for each one of those objects in the table, it checks to make sure that the plays is above 200. So, as you might expect, if we run this against the data, the table that I have, you'll see that the plays indeed have been sort of whittled down to adhere to the restriction, the criteria function passed into the restrict function. And again, going back to an SQL analogy, this is the kind of thing that we would do in a where clause. We would say, where the place is greater than 200 to limit the kinds of results that we get out in the end. So that's kind of the way of viewing a very simple data structure, an array of objects, and applying higher level thinking to it in order to slice it up, get at it, and reason about it in different ways. Ways that something is low level is, say, the cell function would be cumbersome to use, and in ways that sort of you can use to build bigger level ideas out of. And as you recall, the bigger idea that I'm talking about is shown in the previous slide, where we have this data and we want to slice it up in a certain way. So that's the higher level idea. Whereas before it was I built the getArtist function that was really a very straightforward and single-purpose function, whereas these three are very generic and can be used to slice up the data in arbitrary ways. So, and that's where I'm kind of going with in this next part, and that is abstractions built from functions, specifically functional composition and pipelines. So, if you look at a function, like if you wanted to count the number of entries that come out in the artist column. So you get the artist column and you just do a size. And again, underscore has no idea about this table abstraction. It's just counting the size of arrays. So we can use that. And so the number of artists in our table was 4. So if you remember, the way that the functional programming, the earlier functions worked, is that they were strung end to end, deeply nested in this kind of way. In the opposite way of we might be used to thinking about it in say an object-oriented language, or even in the English language. We would say it's opposite in that the inner thing is the thing that happens first, the column extraction, and then the last thing is the next thing is the thing on the outside. So that's kind of twisted around, right? But there's a way of building functions in underscore proper that can take advantage of the idea, the deep nesting, the nested way of thinking about it. So if you wanted to compose a new function, build a new function out of the column, the cod.call function and size, you would pass it into compose. And that highlighted area would return a new function, which is those two functions strung end to end, just like we would do if we were calling them. And then that function that's returned is then passed the table and the column that we're looking up. So, seeing again, composing those same two functions and calling them gives us the same answer as actually calling them in a nested way. So if you wanted to really line those up and see how they aligned, a compose looks almost exactly the same way as it would look if you were calling it in a nested way. The first thing that happens is the call function, and the next thing that happens is on the left, which is the size function. And again, so compose would say the thing that happens first is on the right side, and the things that happen after that proceed from right to left. So a lot of people get a little bit confused by compose because it sort of does things in that inside-out fashion. But if you think about it in terms of a normal function call, it seems pretty straightforward, I think. And hopefully aligning it in this way helps to illustrate that. And how this works is, how compose works underneath is that you have to do a little bit of thinking on your part and understand that you can't just compose arbitrary things, because the input to one function, which is the left side of the cod.call image, and its return type, which is that little thing, the little return type on the right side, and the thing that size would expect as its input value. So in order to make compose work properly, is to ensure that those input and output types align properly. Now, with COD, that's pretty easy because it's always returning the same kind of abstraction, the table abstraction as it goes. So another way to get at the same kind of thinking is that is illustrated in a pipeline, and pipeline is not included in COD my COD library, but it is included in my Lemonade library and the _contrib library, although they take slightly different forms. So I'll show the one that in the Lemonade. I think it's a little bit more clear what's happening. So again, this has taken that idea of that inside-out reasoning about how functions compose, and just sort of using some logic, reduction logic on the inside to make it flow from left to right. Now, so in the pipeline, you would read it as take the iTunes library, pass it in to the cod.call function. Now, there's a little trick happening here, and I'm not really going to talk about that much in this talk, because I don't think it's extremely important for understanding the shape of functional programming, but it's a powerful technique, and it's called currying. And basically what currying means is for every logical argument that you would have in a function, you would keep returning functions that would reduce on those logical arguments until it received all of the logical arguments, and in which case it would perform an execution. So what's happening here in the COD call function is that I'm giving it the less number of arguments than it would normally expect, which is a table and a string. And because I'm giving it less number of arguments than it would normally expect, it knows that, well, you're not quite done with this computation. So I'm going to return a function, a curried function, that will let you later on call and perform the rest of the computation. So that's really all that currying is a way of deferring execution until all of the arguments are received. I'm probably running into a case of libel here by trying to boil it down as simple as that, but it's not much more complicated than that if it is more complicated. But in any case, the pipeline takes that table and then passes it into the function that the cod.call returns, and then passes it into the size function that provided an underscore. And you can see if I execute that, it gives me the same answer as all of the other ones. The same answer is doing the exact nested calls. The same answer is the composed function, and but it's a different way of reading it. Now, this is actually the final slide in the presentation, and I think it kind of throws a lot out there, and I think I've kind of played a trick on everyone by saying, like they do in cooking shows, where they talk at length about the recipe of some piece of some food, and then they show you, the beating the eggs and mixing in the cream, and then, hey, check this out. I just happen to have a cake in the oven, and this is what it looks like in the end. So this is my cake that I've been sort of leading up to, but I'm going to walk through it and really try to give an idea of exactly how, using all of the techniques, simple data, simple functions, building larger abstractions out of the simple data, and building larger abstractions out of simple functions, and then composing them all together via a pipeline in this case, we can kind of achieve what I think is a pretty fluent interface for slicing up data in a functional way using JavaScript. So this first function, I'm just building up another way that would be helpful in building up these larger abstractions is just something as simple as renaming. Renaming a function, giving a function a name, that makes sense in the context of the larger abstraction. So what I've done here is I've created a function called order by, which is almost exactly what you would see in an SQL statement. And I've built that up via this function in Lemonade, which is the currying function. If you recall from the last slide, I talked about how currying is that way of deferring the computation until all of the arguments are given. And so the currying in this case is taking the underscores sort by and returning a function that will take at a later date an array and then sort it by another argument that it will get. I'm sorry, I said that backwards. It returns a function that takes a function and then later on will accept an array, which it'll use that function to sort. Excuse me. What currying2 means is it just means it's applying the arguments in a deferred fashion from right to left, and it only expects a function that takes 2 arguments. It's maybe not the most artistic name that I've ever come up with, but it's functional, so to speak. Taking all of the things that I've shown and some clever renaming, and COD in the library itself uses functional composition, clever naming to build functions named in such a way that you would actually see in an SQL statement. So the select here is basically just a renaming of the project function. It's also curried, but that's less important right now. But I'm not doing anything magical. I'm just giving it another name, and so the pipeline takes the iTunes table, passes it into the select function, which itself is a function that will filter on artist and plays. And it will then pass that into the function the as function, which is built from the rename function that I showed earlier. And the renames are given right there. Any instance of artist will be changed to band. The result of that, the resulting table from that, let me say, will then be passed into the where function, and the where function is just the restrict function that I showed earlier. That is given a special function I didn't really show in this talk, but the field function just takes an object and returns a field. Basically, that's all it does. Filtered on which with what this L.gt is just greater than. It's a function that's just an abstraction for the greater than operator, and finally passes that into that table, the restricted table, into the order by function, which is just built up from sort by. And if you recall, sort by just works off of arrays. So the abstraction that was built up is almost exactly the same as something you would see in an SQL statement. And when you're building up functional, when you're building up your programs using functional techniques, very often you'll find that you're striving to achieve a level of declarativeness in your programs, and that you can't always achieve, although libraries like jQuery try really hard via method chaining to provide this kind of declarativeness. But it's working off of these wrapped objects, but really what I've shown here is that you don't have to do those kind of tricks. You can work off of the raw data using the idea of that higher level abstraction as a guide for how things compose, how functions are strung end to end. And so evaluating that probably it gives us exactly what we might expect. A new table ready to be passed on to the next pipeline. So